Right, this is a quick mini lesson on section 5.4, correlation coefficient, and we're going to be doing hypothesis testing for correlation significance. So the correlation coefficient measures the strength and the direction of the linear relationship between two variables. This is we're referring to the sample. We're taking a sample and we're calculating and measuring R because we want to know something about rho. That would be the correlation coefficient of the population. So they both mean the same thing. Correlation coefficient for the population is rho. Correlation coefficient of the sample is R. So they're both measuring the strength of the linear relationship. So the value of R is always between -1 and +1. And remember, I told you, if you break it into two pieces, the negative sign just tells us that we have a negative slope. And the positive sign means that we would have a positive slope or linear relationship between the two variables. Then the number or the magnitude of R, the closer it is to 1, tells you how strong the relationship is. So for instance, in this scatter plot on the left, as x increases, y is also increasing, right? X increases, y increases. This has got a positive slope. And then we want to look, how close are these dots to this line of best fit? In class, we kind of talked, maybe this is like, I don't know, like 0.75. But it has a positive sign, and then the number, the closer it is to 1, says how strong the relationship is. If it was exactly equal to 1, all those dots would lay exactly on that line. That would be a perfect positive correlation. But the same thing for rho. If all the data laid on that line, we would have a correlation of 1. So exactly as x changes, y changes. So think of rho and R go together. All right, in this case, the second example, as x is increasing, we can read from left to right, right? X increases, y is decreasing. This has got a negative slope. This R would have a negative sign in front of it. And this, I think, actually, these dots are closer than it was over here, so maybe this is 0.85. All right? The bigger the magnitude of this number, the closer the dots are to the line. The sign tells us whether it's an increasing or decreasing line. And then if rho or R equals 0, this is what it looks like. There's no correlation. There's no relationship. There's no pattern. This is rho or R equals 0. So let's look how we do a test of significance. We have a population. We're interested in whether or not the two variables, x and y, are correlated. So when we're looking at the population, rho represents the correlation coefficient of the population. So we take a sample. When we take a sample, we calculate R to see what that looks like. We want to know if that will represent the correlation of the population. We're always going to write our null and alternative for a correlation test of significance like this, always. The null hypothesis is that rho equals 0. If rho equals 0, there's no correlation, okay? This is rho equals 0, R equals 0, no correlation. Our alternative is the test for, is rho not equal to 0? All right, not equal to 0. So somewhere between one of this option or this option. We just don't know how close to the line is. We're just saying that we would have evidence that it's not equal to 0. If rho does not equal 0, then there is correlation between the two quantitative variables, in this case, x and y. Let's look at a quick example. This is from the written homework in section 5. So we want to determine, is there a linear correlation between two variables, x and y. We have a significance level of alpha, and here's our data. So for our null hypothesis, we say rho equals 0. This is what rho equals 0 would be. There is zero correlation, okay? This means correlation, rho equals 0. This is what it looks like, no correlation. We can create this in Rossman Chance. We can create what no correlation looks like. What we're testing is, and this is kind of counterintuitive, the alternative says that rho doesn't equal 0. Well, if it doesn't equal 0, it means there is some correlation. It looks like a line. R is closer to 1, okay? It could have a positive or a negative sign, right? This case it would be a positive R. This would be a negative R. But the alternative means that it doesn't equal 0, the correlation coefficient. Let's look at this data. So if we take this data here, I've got Rossman Chance open. Let me pull that up. Here's Rossman Chance. I cut and paste that data already here. I'm going to use that data. It created the dot plot. I'm going to click on correlation coefficient. That's my R value right here. Okay. Then I'm going to click on regression table as well. All right, we'll go back to that in a second. So my R value is 0.096. 0.096. Now it says find the p-value for the correlation coefficient using a theory-based approach. So when we use a theory-based approach, what I told you in class was let's generate both the simulated approach and the theory-based approach. So we have to go over here and click Show Shuffle Options first. Okay, so when we do that, we want to create what no correlation looks like. And what we want to key in on for the theory-based approach is the t-value of the explanatory variable. See this column heading t statistic? We want to pull it here, 0.27. So we want to choose a t statistic. We're pulling the t statistic from here on the left, and we're going to put it over here in the box, 0.27. All right. This sign always matches our alternative hypothesis, which is two-sided. And then we're going to click here to come up with the theory-based p-value. So it's going to give us both. When we did the simulated value, it gives us 0.71. When we do a theory-based value, it gives me 0.7940. Okay, so this is 0.7940. That's my p-value. P-value, we always compare to our alpha, 0.1. This is way bigger. P-value 0.7940 is bigger than 0.1, meaning that we say that the null is plausible. What is the null hypothesis? Here it is. The null hypothesis is rho equals 0. There is zero correlation between x and y. It is plausible that there is no correlation between x and y.